So this recording is part 2 of part 2, the second half of part 2 notes. It's going to be a little bit quicker than the partial pressure part. I don't have quite as many examples to show you. So what we're talking about here is the collection of gas over water, the collection of gas by water displacement in the lab. And so what you've got going on in this picture is a reaction happening between zinc metal and hydrochloric acid. And zinc metal plus hydrochloric acid is going to make zinc chloride plus hydrogen gas. And if you wanted to collect that hydrogen gas and determine what volume of gas did you produce, one way to do that would be to collect it kind of underneath the water, collect it over water by volume displacement. So you would set up a closed system with some sort of glass tubing leading from the reaction mixture container, and then you would put that tube underneath the water, and in the water you would have some sort of gas collection chamber that originally is going to be filled all the way to the top with just water. You don't want any air in this collection chamber, because you want any gas that comes into that collection chamber to be the hydrogen gas that's produced from the reaction. Okay? So once your reaction starts going, the gas will come over here and it'll bubble through the water, and it will push, by displacement, it will push the water that is in this gas collection chamber out. Okay? And then eventually, when there's no more gas to be produced, you'll kind of hit an equilibrium volume in your gas collection chamber or cylinder. Okay? So that's just sort of give you an idea of what I'm talking about when I say collection by water displacement or collection over water. So when you're doing that type of gas collection, the gas that you get, let me go back, the gas that you get at the top of the cylinder is primarily the gas that you're producing, but some of it will be water vapor that forms. So some of this water will have enough kinetic energy to escape the liquid phase and go to the gas phase and become a vapor. So even though most of the gas up here is the hydrogen gas that you made from the chemical reaction, some of it may be water vapor. So you have to account for that. So the gas that you collect is not called dry. It's not dry gas because there's some water vapor mixed in with it. If you attempt to collect pure hydrogen, then you're actually going to get mostly pure hydrogen with a little bit of water vapor. You can get an idea of how much water vapor is present by looking at the water vapor pressure at various temperatures. So what I'm showing you right here would be something that you would be given in a problem, or you'd have a table of values that you would look up. Okay, it wouldn't be something that I would expect you to know just off the top of your head or from experimentation. Somebody's already done the experiments to get this. So what you would look at is say, okay, I need to know what temperature that I collected this gas at, and then I match my temperature. So let's say I did this at 35 degrees Celsius. The vapor pressure of water at 35 degrees Celsius, and this I'm looking at kilopascals. So at 35 degrees Celsius, the vapor pressure of water is 5.6 kilopascals. So that would be the pressure of water, or the pressure due to the water in the collection cylinder. I'm going to show you how that's used and why that's important. So before we go into the math part of this, ask yourself, why is it logical to expect that the vapor pressure of water would increase as the temperature increases? If you look back here, as the temperature of a reaction mixture increases, the vapor pressure, or the pressure of water, also increases. So why does that make sense? Well, if you think back to what we talked about with our gas laws, as temperature increases, you're increasing the kinetic energy of your water molecules. And when water molecules gain kinetic energy, they can start breaking attraction, so they can get away from other neighboring water molecules. And when they can get away from those other neighboring water molecules, then they can go into the vapor phase. They can make water vapor. So the more energy they gain, the more kinetic energy they gain due to increasing temperature, more and more water molecules can escape the liquid phase and go into the gas phase. So as they go into the gas phase, the pressure increases because pressure is due to moles of gas in a given volume. So as I just kind of explained that, and I'll show you the answer for that in just a sec. But as the temperature increases, the water molecules have enough kinetic energy to overcome attractive forces, and they'll go into the gas phase. And the more gas you have, the higher the vapor pressure gets. So if you were given a particle diagram, which I know how much you love particle diagrams, but they're going to be with us throughout the course, so it's good to kind of keep sharp on those skills. So you've got two containers, and both gases were collected over water. Both contain gases that were collected over water. And you want to know which gas A or gas B, is collected at the higher temperature, and explain your answer. So if I look at this, I would say, well, gas B has been, you know what, I think I did my answer wrong earlier this morning. Yep, I did. You need to look at your particle diagrams, which I did not. I just was in a hurry. Gas B is going to be collected at a higher temperature because if you look at this, I have 1, 2, 3, 4, 5, 6, 7 particles of gas A, and 1, 2, 3, 4, 5, 6 particles of gas B. Okay, there's a little bit of difference there, but what I'm really interested in is the water. So I only had 2 molecules of water here, but in this container I have 1, 2, 3, 4. So the water had to be at a higher temperature to cause increased water molecules to go into the vapor phase, to become water vapor. So actually gas B would have been collected at a higher temperature. The fact that there are fewer gas B atoms or particles or molecules doesn't matter, because I don't know, gas A and gas B are probably 2 different gases, so I may have different amounts of each to start with. So here are your answers, but I was a dummy and picked this first container. It should actually be the second one. So make sure you listen to this and change this. I wasn't thinking this morning when I did this. Okay, and I'm gonna skip this part for right now. It's just a subtraction thing. We'll go over it in class. So water displacement, and sometimes you'll see it in this setup where you've got like a test tube and a Bunsen burner, and then some sort of reaction going on, and the Bunsen burner gives the reaction enough activation energy, enough energy to get the reaction to go, and then you would produce oxygen gas, and the oxygen gas would bubble through the water and displace it in this collection chamber. So water displacement, again, is a common method to collect gas by water displacement. Some of the pressure, though, of the collected gas up here is not necessarily due to only your collected gas that you're trying to get, but it's also due to the vapor pressure of water. So in order to correct for that, you have to look up, or it'll be embedded in your problem, the vapor pressure of water at that temperature and subtract the total pressure minus the pressure of the water to get the pressure of the gas that you're interested in. So if we look at this problem, you have a sample of solid potassium chlorate that gets heated in a test tube, and then it's decomposed over a Bunsen burner by the following reaction. So the potassium chlorate decomposes into potassium chloride and oxygen gas. So the oxygen that is produced in this reaction is going to be collected by the displacement method at a temperature of 22 degrees Celsius and a total pressure of 754 torr. Give me 1 minute. So this value, sorry, this value right here is P total, the total pressure, okay? The volume of the gas collected, so the volume of the oxygen gas collected is 0.650 liters, and the vapor pressure of water at 22 degrees Celsius, which is the temperature that my reaction happened, is 21 torr. And I want to calculate the partial pressure of oxygen first, and then I want to figure out the mass of the potassium chlorate that decomposed. So I'm given two pressures. So what this means is that, let's scooch back here, the total pressure of the gas in this part of the container was 754 torr. But at 22 degrees Celsius, which is the temperature of this water bath, 21, sorry, all this writing's horrible, I'm trying to do this on my mouse pad, 21 torr to 21 torrs of pressure is due to the pressure of the water vapor. Well, I don't care about the water vapor. I just want to know what's the partial pressure of the oxygen gas. So what I need to do, I need to subtract. I need to do the total pressure minus the pressure of the water vapor, because remember, the total is both the oxygen that I produced and the water vapor that was in the cylinder. So I subtract the total minus the pressure of the water vapor, and that'll give me my oxygen gas. So I've done that for you here. Total pressure is the oxygen and the water vapor pressures. So just the pressure of the oxygen gas is total minus water vapor pressure. So the oxygen gas is 733 torr. And I went ahead and converted that to ATMs because I knew I was going to have to figure out the mass of the potassium chlorate that I started with. So I needed to be able to go from pressures to moles to grams. So I'm going to use PV equals nRT. And what I need to do is I need to convert the pressure of oxygen that I have into moles of oxygen. So I'm going to solve for moles of oxygen. It's equal to pressure times volume over R times temperature. So the pressure is what I got. The volume, I collected 0.650 liters of oxygen gas, okay? R is a constant. And then the temperature, this happened at 22 degrees Celsius, so I have to change that to Kelvin, so 295 Kelvin. So total, I produced 0.0259 moles of oxygen gas. And then by stoichiometry, you can work from the moles of oxygen gas to moles of potassium chlorate, and then finally grams of potassium chlorate. So you had to decompose 2.12 grams of potassium chlorate in order to make 0.964 ATMs of pressure for oxygen. And that concludes the part 2 notes. So we'll go over some stuff in class tomorrow if you have questions. But tomorrow's going to be a work day for you in class to work on these problems and make sure that you're straight in your mind with what's going on. So you have a KIA on this information. The KIA just covers part 1 and part 2. Okay, so if you feel confident, you can go ahead and try the KIA tonight, but if not, you can wait till tomorrow. And it's due tomorrow night at, it will be Thursday night at 11:59 p.m. So just let me know if you have questions, and thanks for watching.